Good afternoon viewers and welcome to the EduSat lecture for the science stream. Today we have with us Dr. Amit Kumar from the Department of Chemistry, Dayal Singh College, University of Delhi. He has been teaching us concepts of thermodynamics. We have done the first law of thermodynamics. We have understood about the Joule-Thomson experiment in the last lecture, and beautifully he has explained the application. In today's lecture, he will be introducing the concept of entropy and also the second law of thermodynamics. So over to Dr. Amit Kumar.
Thank you, Unnati. First of all, I wish very good afternoon to all my viewers. Dear friends, we have already covered, as Unnati has said, a number of topics earlier, and today it is time for us to switch on our attention to the second law of thermodynamics after having completed the first law of thermodynamics and its application completely in all respects. Well, the second law of thermodynamics, basically why we need that, this is one aspect we are going to cover in this lecture. What was the limitation with the first law of thermodynamics, what queries the first law of thermodynamics did not responding to, as a result of which we had to look for another law in terms of the second law. This is one aspect we are going to cover in this session. We would also try to envisage certain natural directions or natural changes. What are they? We would also first of all try to see what are natural changes, and on the basis of the observations being made on natural changes only, we would see that there is certain direction associated with natural changes, and in order to address to the direction associated with these natural changes, we need a second law of thermodynamics. So let us first of all make certain observations. Natural direction of change, what it is, what we mean by saying natural direction of change. If we want to understand this, we need to look at three different examples. As you can see, one is written the bouncing of a ball on a hard floor. The second one is when you rope in a plant, then a sapling, and then become plant, then grows to tree, and the tree blossoms, bear fruits and shed its leaves. This is another natural change which we can see. And another natural change which we can view is that an isolated metal hot, which is when heated, gets initially hot at one end and cold at the other, and it finally comes to a uniform temperature if it is kept just for long. So these are the three observations. Let us look at them with a detailed view of what these natural changes are. Suppose we have a hard ball which is being placed at a height h from the floor. Floor is also a very hard floor. When we release the ball is released, and then the energy which is stored as its potential energy now starts getting converted to the kinetic energy, and the ball is set in motion. The ball falls downwards towards the floor. So the potential energy which is stored in the ball gets converted to kinetic energy, and when the ball hits the floor, then it again rebounds. But when it rebounds or rebounces, then it does not acquire the same height at which it was placed initially. What it does mean? It does mean that when the ball strikes the floor, it makes an elastic collision. What it does mean that some of the kinetic energy associated with the ball, that energy has been transferred to the constituent chemical species within the floor, and that gets transferred in the form of thermal motion, or in other words, in terms of thermal energy of the constituent chemical species present in the floor. Now when the ball again bounces, then it certainly makes several couple of bounces and ultimately comes to a rest on the floor. This is the observation. So what it does mean? It does mean the potential energy which was stored in the ball by virtue of its height gets converted to its kinetic energy first when the ball was released, and ultimately the ball comes to rest on the floor, and its kinetic energy is being transferred to the chemical constituents present in the floor in terms of their thermal energy, or to say directly, heat. But has anybody seen that a floor which is hot, which is heated, and the ball is lying on the floor, and by virtue of absorbing that heat, the ball bounces spontaneously? Has anybody seen that? Nobody has seen that. So this is one observation, that there is only one direction associated with a natural change, that is the bouncing of a ball. Now coming over to the second observation. Similarly, a tree blossoms, bears fruit and leaves, and thereafter the leaf sheds as dry leaves and fall on the ground. Has anybody seen the dry leaves attaching themselves spontaneously to the branches and ultimately becoming the buds? Nobody has seen that. But if we see both these observations are in accordance with the first law of thermodynamics. We will come to that. Let us first of all take another observation, and is that suppose we have a steel rod or a metal rod, any metal rod, we heat it to one end. So the metal rod which is heated initially at one end acquires a uniform temperature if it is placed in isolation. Uniform temperature means one end was heated initially and one end was cold, and after a certain period of time, when it was placed in an isolated system, the steel rod develops a uniform temperature. Has anybody seen that the steel rod or any other metal rod which is present at a uniform temperature developing a hot and cold region? Has anybody seen it? Nobody has seen it. But let us now view it from the viewpoint of first law of thermodynamics. What the first law of thermodynamics says? It says energy can be transformed from one form to the other provided that the total energy of the system remains conserved before and after the conversion. So it means the first law of thermodynamics does not place any restriction on the conversion of one kind of energy into the other. As a result, if you see the first observation, bouncing of ball, second observation, the shedding of leaves as dry leaves from the branches, and the third observation, that the one end hot, one end cold of a metal rod acquires a uniform temperature. All these are one directional changes. The opposite direction change never is been observed. But let us view it from the viewpoint of first law of thermodynamics. First law of thermodynamics does not place any restriction on the transformation of energy in opposite direction. So it does mean first law of thermodynamics does not explain these observations as to why these natural changes occur only in one direction. Why not they occur in either direction? So this is the limitation of first law of thermodynamics. Having said this, now question arises, if first law of thermodynamics does not address this and does not put any restriction on the conversion of energy, do we have some state properties, or can we think of some state properties associated with the system which would change in one direction when a natural change occurs, or a change occurs in its natural direction, or real change occurs, or it would change otherwise? That means a certain property associated with the system, it increases with one direction of change, that is natural direction, and it decreases if the change we envisage for a particular transformation of the system is not the natural direction, or in other words the opposite to the natural direction of change. If it is so, then it means that things would get very simple. That is, we need some state properties which talk about this, which provides us an idea and which makes a decision as to the change which we have envisaged for a transformation of a system is a natural direction or in a direction opposite to the natural direction. Inside several textbooks you will also find natural direction being also named as real changes and unnatural changes as unreal changes, or spontaneous and non-spontaneous changes as well. So, now the question is, can we have that kind of state property? The answer is yes. It is the second law of thermodynamics which forms the basis of the concept of such a state property of the system, and it is called the entropy of the system. And now, if you talk about entropy, students always find themselves in a catch-22 situation. If they are asked what is entropy, then they have only to say that entropy is the degree of randomness of a system. Basically, if you need to understand what is entropy, or if you want to answer what is the question in terms in itself is a vague question basically. If you say what is entropy, there is no logical answer to this what is entropy. The real question is that how the entropy changes when a system undergoes a change in state, because what we want to do with this entropy, we are saying that entropy is such a state property, a change in which can be perceived and can be used to make a decision whether the change which we have envisaged for a transformation of a system is a natural direction change or not. So, therefore, better question is, we should ask not what is entropy, we should ask that how the entropy changes, or what is the quantity of what is the change in entropy when a particular transformation occurs in the system. This is the question we should ask if we really want to understand what entropy actually is. And if we ask this question, we can make several physical interpretation about entropy if we know the answer to this question. So, therefore, this is the question we would want to address. And if we want to address this question as to how the entropy changes when a particular transformation in the system occurs, then we should make a we should lay foundation for the mathematical basis of entropy, or we should lay the foundation for the mathematical definition of entropy. And in order to do that, that is best understood in terms of certain cyclic transformations of system. And for the time being, let us switch over our attention from this entropy straight away the second law of thermodynamics to some cyclic transformations of the system, using which we would finally come to define what is entropy, and we would finally see how it decides about the natural changes. So, let us talk about the cyclic transformation of system. In the early 19th century, there was a French scientist, Carnot, who basically was interested in investigating the principles governing the transformation of heat to the mechanical energy, that is work. That was his basically investigation, and he based his investigation on cyclic transformation of a system. And the cyclic, we can just have a look at. In the cyclic transformation which he envisaged, he formulated a cycle that is now known as Carnot cycle. It consists of 4 reversible steps, and therefore the cycle he is envisaged is a reversible cycle. And these steps are: first, the isothermal expansion of a system, followed by second step which is being the adiabatic expansion of a system, then follows the isothermal compression of the system, which is being followed by adiabatic compression, and finally the system is restored to its initial state. Since all these steps are reversible in nature, it does mean that the cycle he envisaged is also a reversible cycle. We have already discussed what we mean by thermodynamic reversibility. So, let us have a look at what way the transformations in this cyclic process occurs. But before that, let us also make a point here that the mass of the system remains fixed during these transformations. What we mean by saying is that we are addressing a constant composition system, and if so, we have only 3 thermodynamic state variables in order to define the state of system, and these are temperature, the pressure and the volume. And if 3 thermodynamic variables are there to define the state of the system, we can make use of any two. The third one automatically gets fixed through the relationship that is called equation of state. So, we need to look at only the variation in the 2. So, it does mean that we can envisage these expansion and compression process on a 2-dimensional curve, that is a curve between pressure and volume, if we choose that these ones are varying. Or third one would also vary, but third one, if we know the value of pressure and volume of the system, the third one, the temperature, would automatically get a fixed value, which we can determine from equation of state. So, therefore, we would not require to specify it. The 2 are sufficient to define the state of system. So, let us say the system, when is present initially in its initial state, has temperature T1, the pressure P1 and the volume V1. This system undergoes, as I said, the first step, that is isothermal expansion. Isothermal expansion means the temperature of the system remains constant, and therefore, the final state which it acquires during this first step is again having the same temperature T1, but the pressure changes from P1 to P2 and volume also changes from V1 to V2. So, this is second state it acquires. Now, after this isothermal expansion step, it follows a adiabatic expansion step from state 2 to state 3. In this transformation, the system is insulated, and therefore, whenever the work is done by the system during the expansion process, the work is done at the expenditure of its internal energy, and the temperature of the system decreases from T1 to T2. So, it means T1 is the higher temperature and T2 is the lower temperature, and it acquires the state 3 where the temperature is T2, pressure is P3 and volume is V3. Now, these are 2 expansion steps which is being introduced to reach to state 3. After this, the system undergoes compression step. This compression step is an isothermal compression step and occurs at same temperature, lower temperature. Now, mind you that T2 is the lower temperature over here. So, at this temperature T2, which remain constant, the system undergoes expansion. The system undergoes compression from volume V3 to V4. So, V4 is a lesser volume as compared to V3, and the system acquires this final state in step 3, that is temperature T2, volume pressure P4 and volume V4. Now, from this state it undergoes again an adiabatic compression in the 4th step, and ultimately the system gets restored to final again the same value of initial pressure, that is P1, temperature T1 and the volume V1. Now, you can notice the temperature during the isothermal compression and expansion steps remain the same. However, when expansion occurs, heat enters the system, that accounts for the energy which is being expanded in order to achieve the expansion process. So, therefore, temperature remain constant in this manner, the heat enters the system. So, in the isothermal compression process, the heat would leave the system because compression occurs. So, therefore, the work will be done on the system and it will raise the internal energy, and by virtue of which the temperature of the system would rise, and in order to maintain the same temperature, the heat would leave the system. So, QC amount of heat would leave the system there then. If we talk about adiabatic steps, the temperature would change. That means, now here during expansion temperature decreases from T1 to T2, and during compression, adiabatic compression process, the temperature rises from T2 to T1. These are basically the 4 different steps which were present in the Carnot cycle. Having said this, now looking at the Carnot cycle would obviously be just a cycle that would be exhibited by a system. That means such a system that produces heat and work effects in the surrounding basically is called a heat engine, and therefore the system which was exhibited in these steps would be termed as heat engine. And you see, in the first and third step, which were isothermal in nature, heat was entering and leaving the system. Now, how the temperature of the system remained constant is that the system was immersed in a constant temperature bath, or we can say heat reservoir. Let us now define again the heat reservoir is a system that has the same temperature everywhere within it. This temperature is unaffected by the transfer of any desired quantity of heat into or out of the system. So, this heat reservoir serves as the immediate surrounding of the system. Having said this, so we have now illustrated the number of steps, expansion and compression steps, which forms the Carnot cycle. This we can see with the help of a pictorial representation also. In the first 2 steps the volume rises, and thereafter the volume decreases. This step volume rises, second step also the volume rises, and third step volume decreases, and fourth step, that is from this state to this state, volume again decreases. Having said this, now it is time to envisage what is the initial and final state. We have already specified. Let us apply the first law of thermodynamics to these steps individually and see what transformations actually occur within the system. You see, it is very sure that whenever a system undergoes a change in state from initial state to final state, there occurs a change in the value of state variables, and it is the first law of thermodynamics which specify the change in internal energy of the system. Now, here we try to calculate the change in internal energy for all these steps using the first law of thermodynamics. The first law of thermodynamics which we are making use of here, it is important to note that this is the first law which is being used in classical physics or used by physicists, because that helps us basically to view the Carnot cycle better. So, I have not used IUPAC system here, but I have used the system of the first law convention which is being used by physicists deliberately. So, here the change in internal energy of the first step, that is equal to the heat exchange by the system with the surrounding Q1. Now, mind you, we have already specified that in this step the heat does enter the system. So, Q1 would be a positive quantity, and W1 minus W1. So, in the second step, the change in internal energy is only equal to the work effect. Why it is so? Because it is adiabatic system. In the second step, the system becomes adiabatic in nature. Adiabatic means neither the heat can leave the system nor the heat can enter into the system. So, heat exchange by the system with the surrounding is 0. So, the first term in this expression has become 0, and that is why delta U2 equal to minus W2. And similarly, in third step delta U3 equal to Q2 minus W3, and fourth step delta U4 equal to minus W4. Now, if we apply the same first law of thermodynamics to the complete cycle, now you see delta U, here it is written 1, but it should not be 1, it should be delta U total. So, there is a little correction over here. Delta U is equal to 0. Why it is equal to 0? Because the system has undergone a cyclic transformation. It started with one initial state, it traverses 3 different states and finally reaches the same initial state. So, in a cyclic process, when the system gets restored to its initial state, system it means does not suffer any change in values of state variables. So, in total there is no change in internal energy. Therefore, delta U of system equal to 0 equal to Q cyclic, that is Q cyclic is the thermal energy being exchanged by the system in this whole cyclic process minus W cyclic, that is the work effect produced. So, we can see Q cyclic minus W cyclic equal to 0 and we can say that W cyclic equal to Q cyclic. Now, this thing we can obtain straight away. W cyclic is the sum of work effect produced in all the steps and Q cyclic is the heat exchanged in all the steps, sum of heat exchange in all the steps. So, we can sum first law being we can sum up all these first law equations and ultimately what we get is W1, W2, W3, W4 their sum is equal to heat exchange by the system in all these steps, and we see there are only 2 steps in which heat was exchanged. Therefore, Q cyclic equal to Q1 plus Q2 and W cyclic equal to all these W1 plus W2 plus W3 and W4, and this actually is equal to Q1 plus Q2. So, therefore, again that Q cyclic is also equal to Q1 plus Q2 and W cyclic is also equal to Q1 plus Q2. Having said this, now we are very near to the foundation of the Kelvin statement of the second law of thermodynamics. Let us see how this Kelvin made the statement. In the Carnot cycle, work effect in the cyclic process is the sum of 2 terms, each associated with a different temperature. What we mean by saying this is that this is the work effect, that is the W cyclic, net work produced by the system or net work effect, that is equal to the sum of the heat being exchanged by the system in 2 different steps, or we can say sum of heat exchanged by the system. In all the steps there are only 2 steps which exchange heat. So, that is the meaning of this statement, that in the Carnot cycle work effect in the cyclic process is the sum of 2 terms each associated with a 2 term means 2 different heat exchanged in 2 steps each associated with a different temperature. So, heat was exchanged at higher temp when the system was present at higher temperature, and heat was also exchanged by the surrounding by the system with the surrounding when the temperature was at lower temperature 1 and 2, T1 and T2, and therefore, heat exchange was Q1 and Q2. Now, we can say that we might now imagine a complicated cyclic system which involve not just these 2 heat reservoirs, but may involve many heat reservoirs at different temperatures. In such a case also W cyclic would also be equal to Q1 plus Q2 plus Q3 plus Q4 and so on and so forth. Now, the idea is that you can easily see when the system was present at higher temperature, heat did enter the system, and when the system was present at lower temperature, heat did leave the system in the Carnot cycle. So, it means one time when heat enters the system, it was having a positive magnitude, it was having a quantity which was having a positive sign, because heat enters the system. When heat leaves the system, it is a negative quantity. So, here also if suppose in this a complicated system where we have so many different thermal reservoirs, some reservoirs will be maintained at higher temperature, some reservoirs will be maintained at lower temperature, heat would enter the system when the system would be in thermal equilibrium with higher temperature thermal reservoirs, and the system and the heat would leave the system when it would be in contact with low temperature thermal reservoirs, or in other words we can say some thermal reservoirs will be there which will supply the heat to the system, and some thermal reservoirs will be there which will receive the heat from the system. So, therefore, it does mean the overall work effect in such a complicated cyclic process would also be sum of such heat effects being produced, and some will have a positive value, some will have a negative value. Now, it is possible to devise a cyclic process so that W cyclic is positive, and either we do that process using a Carnot cycle having only 2 thermal reservoirs, or we can make such a complicated process where we have several thermal reservoirs. There will be positive work effect will be produced, that is work will be produced in the surrounding. Till date, no experience has not shown that we could have a system which would have only one thermal reservoir and which would supply the thermal energy to the system, and using this thermal energy the system would do work. Till the point of time, no such observation is made. And this overall observation that we cannot make such a system which could do work without having at least two thermal reservoirs, one at higher temperature, one at lower temperature. So, this has led to the conclusion, this observation basically makes a conclusionary remark, or basically gives a formulate the almost nearly the Kelvin statement of the second law of thermodynamics. Just have a look what Kelvin has to say. He says so second law of thermodynamics, basically there is no derivation of second law of thermodynamics. I did say in the beginning in my first lecture itself, the laws of thermodynamics are the rich summaries of experience. Whatever is been experienced, that is been formulated in terms of laws, because they are universally applicable, and till date no such observation is being made which provides a contrary to these laws, or where these laws makes a default. There is no such observation is being made. So, now what Kelvin has to say, that it is impossible for a system operating in cycles and connected to a single heat reservoir to produce a positive amount of work in the surroundings. It means that if a system is having a single thermal reservoir such that the system can absorb heat from it, and we can think of producing a positive amount of work in the surrounding, no observation has been made, and hence we have coined the second law of thermodynamics. It is impossible for a system operating in cycles and connected to a single heat reservoir to produce a positive amount of work in the surroundings. So, what we should do? It does mean at least the system should be, if a system is there which operates in cycles, it should be at different point of time, it should be in contact with at least two thermal reservoirs, where it can absorb heat from one thermal reservoir and can reject some quantity of heat which is being absorbed to the reservoir which is being maintained at low temperature, and thus allows the heat to flow from a system of higher temperature, from a reservoir of higher temperature to that of a lower temperature reservoir via the system, and it is the directive influence of heat which basically produces work. So, it means if we want to obtain work out of heat, the heat must flow. That was the essence of this observation, and therefore, I would like to once again make this very clear that these laws are rich summaries of experience. This is just one statement of second law of thermodynamics. There are several Kelvin statement, Planck statement, and then Clausius statement, so many statements which is being made. All these are equivalent statements, all these are being made or based on different observations, and they are just more or less been the same. So, let us make another observation. Experience has also shown that if a heat engine operates between two temperature reservoirs, so that a positive amount of work is produced, then the heat withdrawn from the high temperature reservoir is positive, and heat withdrawn from the low temperature reservoir is negative. It means, as I said earlier, that heat must flow. The system should absorb heat from higher temperature thermal reservoir and should reject some part of it to the thermal reservoir maintained at lower temperature. So, one way it would be a positive quantity, one other time it would be a negative quantity, the heat. Having said this, let us now talk about efficiency of such a heat engine. What is the efficiency of a heat engine? The efficiency of a heat engine, it is given the symbol psi, is defined as the ratio of work produced to the quantity of heat extracted from the high temperature reservoir. That is psi equal to work being produced divided by the heat extracted from the thermal reservoir maintained at higher temperature. Now, work effect we have already seen is sum of these heat effects produced, that is Q1 plus Q2, all such heat effects. So, therefore, work is being substituted with Q1 plus Q2 divided by Q1. Now, this becomes equal to 1 plus Q2 by Q1, and we have already seen this is again based on observation that heat gets rejected to the thermal reservoir which is maintained at lower temperature. In this case is second thermal reservoir. So, therefore, Q2 would be a negative quantity and Q1 would be a positive quantity, and Q2 would be a negative quantity. It does mean Q2 by Q1 would be a negative quantity, and therefore, from 1 some negative quantity less than 1 would be subtracted. So, it means that the efficiency of a heat engine is the fraction of the heat withdrawn from the high temperature reservoir that is converted into work. So, it is again an observation which makes us to conclude that not all the heat which has been absorbed from the high temperature thermal reservoir gets converted into work, but basically it is some fraction of that particular heat withdrawn from the high temperature thermal reservoir can only get converted into work. So, it means this is based on the observation that no such system has 100% efficiency. So, therefore, again we can make another statement of second law of thermodynamics based on this observation. It is impossible for a system operating in cycles and connected to a single heat reservoir to produce a positive amount of work in the surroundings. It must also have a low temperature reservoir where the system can reject heat. The work is produced only when heat flows, and it is the directive influence of heat which produces work. Work therefore has a natural, we all know that whatever amount of work we do, that can be completely converted into heat, but now we can see here the heat is not getting completely converted into work. So, we can say another way, another statement, work has a natural tendency to get converted completely into heat, but the reverse is not true. The heat can never be completely converted into work. So, this makes another statement. Now, since the heat absorbed and the rejected to the thermal reservoirs by system basically depends or is a function of only of the temperature. So, therefore, we can also formulate the efficiency of heat engine in terms of temperatures of the reservoirs with which the system comes in contact, comes in thermal equilibrium, better to say. Therefore, we can formulate psi, the efficiency, as 1 minus T2 by T1. When we will do the thermometry and we will define the absolute scale of temperature, then we will also try to derive this relationship. Now, it is time, if we want to formulate the basis of concept of entropy, that comes from here. When we do make comparison of different expressions of efficiency of a Carnot cycle. Now, you can see two different expressions we have developed for efficiency. One is that psi equal to 1 plus Q2 by Q1, and the other is psi equal to 1 minus T2 by T1. Both these are equivalent expressions. So, we can subtract from equation 6 from equation 7. So, left hand side will cancel. So, therefore, ultimately what we get is 1 and 1 will also cancel, and therefore, if we subtract equation 7 from equation 6, what we get, Q2 by Q1 minus become plus T2 by T1 equal to 0. We can rearrange this equation to get Q2 by Q1 equal to minus T2 by T1, and ultimately we can once again rearrange it in a way that we can say Q2 by, now what we do is we take T2 from the numerator of right hand side to denominator of left hand side, and Q1 from denominator of left hand side to numerator of right hand side, and we ultimately get Q2 by T2 equal to minus Q1 by T1. And therefore, we can rearrange this equation 10 again, we can take right hand side to left hand side, we get Q2 by T2 plus Q1 by T1 equal to 0. Now, you see the left hand side of equation 11 is simply the sum over the cycle of the quantity q by t. What I mean to say by this is we can also represent this sum as the differential of some quantity, that is equation 11 could also be written as cyclic integral dq by t. And it is important to make an observation here that the Carnot cycle was a reversible cycle, all the steps were reversible. So, therefore, this relation holds true only for reversible cycles, it is important to note over here. Now, coming over to the properties of state functions. Since the sum over the cycle of the quantity dq by t, this is a differential quantity, is 0, the quantity is the differential of some property of state of system, that we can say it is the entropy of the system. That is, if suppose we have a state function z, the cyclic integral of the differential dz over a cyclic path becomes equal to 0. This is the properties of state functions which we defined in the first lecture. So, therefore, using which we can say the differential quantity dq by t is a differential of some state property of the system, and that is how we define the entropy of the system. So, this forms the mathematical basis of the definition of entropy. Just have a look. So, the defining equation for the entropy is then ds equal to dq reversible by t. How we should read this equation? It means that we cannot define entropy as a quantity as such. What we can define is that entropy is a state property of the system. The change in entropy for a particular change in state of the system is basically equal to the reversible heat exchange. That is the heat exchange by the system from going from initial to final state, connecting a reversible path at the specified temperature. That is how we must define the change in entropy, and we say that entropy is some state property of the system, and we can define the change in entropy. We cannot exactly give the absolute definition to the absolute quantity of entropy, but we can say entropy is some state property of the system whose change we can perceive as the reversible heat exchanged by the system at a specified temperature. This is how we should perceive the change in entropy. We should not perceive what actually entropy is, we should perceive as how the entropy changes, and we should be able to quantify the change in entropy for a particular change in state of the system. Having said this, now we have just formulated the mathematical basis for the change in entropy of the system. Now, it is time to see how basically the change in entropy forms the basis to decide whether a change in state of the system for which we have quantified the change in entropy, how it decides that the change which we have envisaged in the system is basically a natural direction or a spontaneous change, in other words. Now, next question is this: how the entropy does this serve this purpose for us? In order to understand this, now again consider the Carnot cycle, and we would compare it with some other cycle as well. Let us have a discussion. Let us initiate this discussion now. Again consider the Carnot cycle in the reversible cyclic process. That is, if a cyclic process in the Carnot cycle, work effect equal to cyclic integral dq, that is the integral of the quantity dq over a cyclic path. Now, for such a reversible process, we have just come to the conclusion that cyclic integral dq by t is equal to 0. Now, it is important to note that by definition of a Carnot cycle, Q is a reversible heat exchange. So, whatever dq is written over here represent a dq reversible or a reversible heat exchange with the surrounding. Now, this is what we have again considered Carnot cycle. Now, consider another cycle in again consider some other heat engine, let us say E dash, and let us suppose that this engine E dash, which is not a Carnot engine, which is some other engine, also undergoes some cyclic process. And in the cyclic process exhibited by heat engine E dash, the work effect would also then be W dash, and the differential of which we can again write similarly, that cyclic integral of the differential of heat exchange during this cyclic transformation, that is cyclic integral dq dash. Now here what we suppose, now we do not say that the engine operates reversibly or irreversibly, we do not say this. So it means that the cyclic integral dq dash by t, which was 0 for a reversible process, here because we are not saying that this engine E dash operates reversibly, it does mean that it can have any other value, may not be 0. Let us suppose it is greater than 0. If it is greater than 0, then this engine may have, again similarly as the Carnot cycle had two thermal reservoirs. So this engine may also have 2 or more than 2. Now suppose this is a complicated cycle. This engine traverses a complicated cycle where there are many such thermal reservoirs. If so, now suppose that Carnot heat engine and this second engine E dash are coupled to make a composite engine and make such a machine. Now if they make a composite engine or a composite machine, the work produced by the composite engine would be Wc, that is equal to the work effect produced by Carnot cycle, that is W, plus the W dash, that is the work effect produced by this engine E dash. Now we can get Wc as cyclic integral of dq plus dq dash, which is equal to cyclic integral dqc, that is dqc is the heat effect in, qc is the heat effect in composite system. So now we should add equation 15 and 17. What are these equation 15 and 17? Let me make it once again clear. This was for a Carnot cycle. We had just derived that cyclic integral dq by t is equal to 0. And we have assumed that for this engine E dash, cyclic integral dq dash by t is greater than 0, non-zero quantity. So it does mean that cyclic integral dq by t and dq dash by t for this composite cyclic engine, the first one dq by t is equal to 0 and dq dash by t cyclic integral is greater than 0. So for this composite system should also be greater than 0. If so, we can say that cyclic integral dqc by t is greater than 0. So we may now adjust the direction of operation of Carnot cycle such that composite engine produces no work. What we mean by saying is that we have a Carnot engine and we have another engine E dash, both have been coupled and they make a composite engine, and when they make a composite engine, we suppose that they do not produce any work effect in the surrounding. They do not produce any work effect in the surrounding. And in doing so, it means the work required to operate engine E dash is supplied by the Carnot engine or vice versa, or in other words we can say the work required to operate Carnot engine is being provided by E dash, or the work required to operate E dash is supplied by Carnot engine. This is vice versa, it could be either way. So we have just assumed that suppose that work effect produced, net work effect in the surrounding produced by this composite engine is 0. If so, since work effect of the composite engine is 0, this is equal to Wc equal to cyclic integral dqc, and therefore this should also be equal to 0. So this makes equation 23. Now again consider this, we had assumed the equation 17, cyclic integral dq dash by t is greater than 0. Because this was equal to 0 for the Carnot engine, for this engine E dash we had supposed that cyclic integral dq dash by t is greater than 0. Now the question is, under what conditions will these relations given by equation 23, that is the cyclic integral there is of dqc, heat exchanged by this composite system in all such steps is equal to 0, and second is what we had assumed, the cyclic integral dq dash by t is greater than 0. Under what conditions will these relations be compatible? Now we have to ask this question. In order to answer this, we can expand these ones. Cyclic integral dQc equal to 0 means, if suppose there are several steps in which heat is being exchanged by this composite system, it means Q1 plus Q2 plus Q3 plus Q4, all the sum equals to 0. And the equation 17 says cyclic, which we had assumed, the cyclic integral over dq dash by t for the engine E dash is greater than 0. So it means dq by q1 by t1 plus q2 by t2 plus q3 by t3 plus q4 by t4, all their sum should be greater than 0. Now, it does mean when q1 plus q2 plus q3 plus q4 all their sum equals to 0, the left hand side of equation 23 is a sum of heat exchange in many of the steps which these composite systems undergo. This equal to 0 means, it means therefore mean that some q's will be positive and some q's will be negative, then only the overall sum in the equation 23 would be equal to 0, and then equation 23 would satisfy. So it does mean that similarly, if we want to satisfy this, then we also need to satisfy equation 17. What equation 17 says? Q1 by T1, Q2 by T2, Q3 by T3, Q4 by T4, their sum should be greater than 0. If some q's are positive, some q's are negative, then it means in equation 17 also some terms would be positive and some terms would be negative. It does mean that suppose those terms in which q values are higher, they are positive, and those q's which are negative, they are smaller. Or in other words, we should search for the denominator values, that is the temperature values, which would make the overall sum, the positive terms, predominate over the negative terms. That is possible only when, if we divide higher quantities of heats, positive quantities of heats with lower values of temperature, and we divide negative quantities of heat with higher values. That is how positive quantities will predominate over the negative quantity and will satisfy equation 17. That is to say, the overall sum of all these terms would be greater than 0, would be a positive quantity. What it does mean? In doing so, what we have done? We have done one thing, that is we have associated positive quantities of heat exchanged with the system, that is when heat enters the system, with the smaller values of temperature. That is, we have associated absorption of thermal energy by the system from reservoirs which are maintained at lower temperature, and we have associated negative quantities of heat, that is when the heat is rejected to the surrounding or to the reservoirs that are maintained at higher temperature. It does mean the system absorbs heat from extracts heat from low temperature reservoirs and rejects it to high temperature reservoirs. If we can make such a machine, a composite system, where one part of it can be out of the room, one part of it can be inside of the room. In the winter, temperature outside is cold, lesser, and temperature inside the room is higher. What it would do? Let us apply this machine, and the machine will extract heat from low temperature reservoir, that is from the surrounding, and will pass the heat to the high temperature reservoir that is within the room. So it becomes a all weather AC without expenditure of any electricity. In the summer, we can operate the machine reversibly. That is, the machine is put in a way that from the higher thermal reservoir outside the surrounding, outside of the room, the heat is being rejected, and from inside of the room where the temperature is already lesser, heat is being extracted. So it makes such a machine makes an all weather AC without having any any application of electric current? The question is, nobody in the world has made such an observation. So, this is false. So, all this mathematical business which we have done in this whole derivation, what went wrong? The question emerges now. Idea is that our assumption that for engine E dash, we had made an assumption that cyclic integral dq dash by t is greater than 0. And we had said therefore that these terms having a magnitude greater than 0, a positive value. This was therefore, this is where we went wrong. So, it does mean that for any kind of engine, we can have cyclic integral dq dash by t value never ever greater than 0. It may have a value either less than 0 or it may have a value equal to 0. As we have seen, for the Carnot cycle which was operating reversibly, the cyclic integral dq by t is equal to 0. So, therefore, for reversible process, cyclic integral dq by t is equal to 0, and for irreversible process, non-reversible process, now we can see it can be either less than or equal to 0, but it should not be equal to 0. Why it should not be equal to 0? Just because of the fact that heat effects produced in a reversible change and an irreversible change are different. So, therefore, since it cannot be greater than 0, so therefore, cyclic integral dq by t in any given engine would be less than 0 at best if it operates reversibly, or the transformations occur in a thermodynamically reversible manner, then it would be equal to 0. And this is a very important equation which would finally lead to a very important concept called Clausius inequality, which will be the signpost of spontaneous change, which will actually make use of entropy and will let us know how we can make a decision on the change which we have envisaged in the system is a natural direction change, a spontaneous change, or a real change, or unnatural change, non-spontaneous change, or an unreal change. So, we will start with discussion of Clausius inequality in our next lecture. Thank you very much.
Thank you, Dr. Amit Kumar, for a very easy explanation of the Carnot cycle. We understood the 4 processes involved in it: the adiabatic, expansion and compression, and isothermal compression and expansion. Sir, I would like to ask one little question regarding the adiabatic compression. So, can you explain that in terms of entropy, because we still haven't discussed the entropy aspect in it?
Alright, you see, if I am being able to understand, as you are asking about what way the entropy changes in an adiabatic compression process. We have just defined and quantified the change in entropy, or that is how we should determine the change in entropy for a system when there is heat exchange, when the system during this transformation exchange heat with the surrounding. So, now when we quantify and when we try to see how we can make use of the change in entropy and link it to the decision whether the change is natural or not, thereafter our job will be to relate this entropy change to the changes in state variables, the temperature and the pressure, and that is how we would be able to better quantify the change in entropy, and in that sense and at that point of time we would be able to determine the change in entropy for this adiabatic compression process also. So, that we would do little later.
Thank you so much, sir. Definitely we will take up this lecture in our further series for better understanding of this second law of thermodynamics. Thank you, viewers. You can look at this lecture at the YouTube channel and do leave in your comments, and if you have any queries, please do write in to us. Thank you.